You clicked this video because your scaling experiments are failing silently. You have 10 GPUs in a cluster, but the performance drops instead of rising. The real stake here is that you might be burning budget on hardware while your workloads crawl at 1/10 of their potential speed. By the end of this explanation, I will show you exactly why standard Kubernetes settings create invisible bottlenecks and how topology awareness changes everything for large-scale machine learning deployments. Many engineers treat GPUs as simple scalar resources just like CPU cores or memory slots. You tell the system you need 2 units of GPU capacity, and it gives you a container running on some available node. This works perfectly fine when you are testing locally or scaling to just 4 machines. The moment you push beyond 10 connected graphics processing units, the underlying physics of your hardware begins to contradict the logic of your software scheduler. Kubernetes provides essential process isolation, but fails at hardware topology awareness and non-uniform memory access alignment. It creates invisible bottlenecks that cause linear scaling workloads to collapse when you cross that threshold of 10 times GPU counts. To understand why this happens, we must look at how modern data center servers are physically constructed inside the rack. A single compute node contains multiple central processing units connected through complex interconnects called PCIe switches. Each CPU socket has its own local memory pool and direct access to a specific set of graphics cards attached via those physical cables. This architecture is known as non-uniform memory access, or NUMA. When your software running on one processor core tries to read data from the memory bank connected to the other central processing unit, it must cross that expensive interconnect bridge. The latency spikes significantly compared to accessing local memory directly adjacent to where you are computing. Standard Kubernetes relies on a device plugin system to report available hardware resources. This plugin tells the scheduler which nodes have free GPUs and how many they possess. It treats every graphics card as fungible, meaning one GPU is functionally identical to any other GPU in the cluster regardless of its physical location or connection topology. The scheduler sees 10 units of compute capacity but has no intelligence about whether those cards are all on a single motherboard or spread across different NUMA domains. When you launch a large distributed training job that spans multiple nodes, it assigns containers without regard for which CPU socket hosts the GPU memory they need to access most frequently. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This lack of hardware-aware scheduling creates suboptimal memory access patterns that destroy performance scaling. Imagine your machine learning model requires constant data exchange between processing units and graphics cards across different NUMA domains. Every time a worker node tries to fetch weights or gradients from a remote memory bank, the system incurs significant communication overhead. The result is nonlinear performance degradation, where adding more GPUs actually slows down your total throughput instead of speeding it up. You are effectively building a highway with traffic lights at every intersection while trying to drive a Formula One car. The native autoscaler also struggles because it cannot accurately predict resource availability or handle the cold start latency required for graphics drivers to initialize on new nodes. When you scale from zero, the cluster often remains under-provisioned during critical scaling events because the system does not know when to trigger a node launch until after the workload has already stalled waiting for resources. This forces infrastructure teams into either over-provisioning hardware to absorb these delays or leaving clusters with insufficient capacity that cannot handle peak loads efficiently. The promise of elastic scaling breaks down precisely when you need it most during sudden spikes in demand. Current solutions often attempt to patch this problem by introducing an adapter layer using tools like K3s and Coder to automate environment reproducibility. These systems successfully streamline driver installation and reduce onboarding friction for new engineers setting up their development environments. However, they remain focused on the initial setup phase rather than solving low-level hardware scheduling challenges during runtime execution. Technical guides confirm that enabling GPUs requires complex modifications to container runtimes like containered, but these efforts frequently result in device plugins failing to report capacity or stalling during initialization. Practitioners working with mixed workloads on shared nodes report unpredictable latency because the system cannot migrate workloads across NUMA domains without significant performance degradation. Without a dedicated layer for topology-aware scheduling, your cluster operates as if it has sufficient raw compute capacity when in reality, the hardware is being utilized inefficiently due to poor data placement decisions made by the scheduler. The disconnect between cloud provider infrastructure and the Kubernetes control plane often leaves device plugins unable to report resources correctly during critical scaling events, masking the true state of your system. Here is where the situation becomes most critical for engineers deploying at scale. There is currently insufficient benchmark data demonstrating specific throughput losses incurred when scaling beyond single-node limits without explicit non-uniform memory access affinity policies. This creates a knowledge gap, where we know invisible bottlenecks exist but cannot quantify their exact impact until after performance has already collapsed. You might see your training job take twice as long to complete with 10 GPUs than it does with 5. Yet no standard monitoring tool will tell you why the extra hardware is causing this regression rather than improvement. The absence of a unified management layer means that while Kubernetes manages processes effectively, it fails at aligning those processes with physical hardware constraints. This leads to scenarios where GPU migration and topology alignment become impossible tasks for operators who are already fighting against configuration complexity. The system masks the true state of cluster capacity because device plugins fail to report resources correctly or stall during initialization, leaving teams unable to utilize available hardware even when it sits idle, waiting for proper assignment logic. Until this gap is filled by explicit non-uniform memory access affinity policies and topology-aware scheduling implementations, your scaling experiments will continue to hit invisible walls that tutorials never mention. The solution requires moving beyond simple resource requests toward understanding the physical reality of how data flows through your specific server architecture. You must account for PCIe switch latency and NUMA domain boundaries when designing your distributed training pipelines if you want to achieve true linear scaling across large clusters. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.